Hello, everybody. Come on in. We got about 5 minutes before class is supposed to start, so feel free to ask me any questions you might have until then. Today, we're sort of rapid fire going to go over chapter 11. And then next time we meet, we'll be covering chapter 36, which is special relativity.
Professor, I have a question about the chapter 10 and 11 homework due dates.
Yes, I changed them right after class on Monday.
Mine still, my homework still says past due
Let's
for
see.
some odd reason.
Yeah, it's still showing me as due on the 2nd as well for chapter 11.
Okay, that's weird. It definitely shouldn't be. Let me double check what's going on here. Oops, wrong thing. I want this. I got that. Okay. So chapter 11. That's odd. Okay. Sorry about that. I must not have hit save or something. Let me go ahead and fix that right now. Sorry about that, guys. 36 is going to change as well, I suspect. Well, actually, that might be okay. But let me go ahead and change this one. So chapter 11, which shouldn't count at all, obviously, because we haven't even covered it yet. But I am going to change that to, we will cover it all today. I'm going to actually make it, you guys meet on Mondays and Wednesdays. So I'll make the conceptual part due on the 11th. And then I'll make homework part due on the 16th. No, the 9th. Oh. Yeah, I'll do the 16th. What the heck? So that looks fine. And chapter 36, I'm going to do both of these on the 16th. I'm going to do this on the 11th. All right. So I think what I have now should work. And if you can't get in it, just let me know. But it shouldn't have any problems letting you back in. I did change the dates. That's weird. I changed all the dates last time too, and it looks like none of those changes. Yep, not a damn one of them. Sorry. Yeah, not a single one worked. I changed all these to like 4:30 because that's literally the last day that you can turn stuff in. So it is not supposed to be like that. Sorry about it. Anybody else have any questions? After 36, we'll go into 14 and 15. So I've got 36 played out here. And what I'm going to go ahead and do is go ahead and make the rest of these dates while I'm waiting on people. I've still got about 1 minute left for class starts, everyone. So feel free to ask me any other questions. 16 is there. 16 is there.
Could I speak with you after class?
Yeah, we can do that.
All right.
And we can do a breakout room too if other people are sticking around. It's not a problem. I'm going to go ahead and change this to the 30th. 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 Let me see what else.
Are any of the chapters that we've been having after the midterm going to have tests like the ones before the midterm, or?
Yes. So I'm actually planning on making a test today that'll cover the next 2 chapters, which I think the last chapter we did was through 8, if I remember correctly. I'm not sure that that's right, but anyways, that's what I seem to recall. So I will be making a test for chapters 9 and 10. If I'm right about those numbers, the next 2 chapters, either way, whatever the next 2 chapters are that we haven't been tested on, I'll probably set those available probably tomorrow, and you'll have like until Sunday of next week, or, you know, not this coming Sunday, but the Sunday after, to get that done. And I'm probably going to make another one as well. So there should be a 10, 11, that might be 10, 11, and 36, or it might be 9, 10, 11, and then 36, 14, and 15. But that's what it's going to be. So yes, I will have some other tests. And in fact, it's not uncommon for me to have the last test due on like 4:30 or 5:1 or something like that. And sometimes I'll even make that last one sort of optional. So I'll drop 2 of your lowest online test grades instead of 1. All right. So anybody else have any other questions? And I didn't see who actually said they wanted to speak with me after class. So you'll have to remind me when I get there. I was just trying to do something else at the time, but not a big deal. You can just remind me then. So one more time, does anyone have any questions on previous material, test, anything like that? I just finished resetting for the second time the dates on the homeworks. The rest of them are set for the rest of the semester, so you shouldn't have any problems here on out, hopefully. And I am going to cover chapter 11. Specifically, I sort of talked about all of it already. When we did gravity, I talked about a great deal of it. When I did rotational motion, I talked about a great deal of it. So I'm actually going to continue from that, as if you sort of know what's going on. I'm actually going to show you a cross product so you can see how that's done and all that good stuff. So it seems like no one has any questions, so I guess I'll go ahead and get started. I'm going to start by sharing my page, or sharing my screen with you. And that's the plan anyways. Okay, so let's turn this up here. Gotta admit another student. Got to add that. Got to delete that page. And that took care of that. Okay. So now I think I got everybody in here. So what we've learned previously is, remember, we had Newton's second law of motion, and Newton's second law of motion originally I worded like this, and basically it was m times dv dt, which you recognize as m times a, and that's fine. I just wanted to reiterate that it's there. What I told you, though, is that actually when Newton wrote it, he gave it more this form. Of course, he didn't really have vector calculus and stuff like that at the time, so it doesn't appear that way. But he basically gave us the power to recognize that it was d by dt of p, and we defined p to be mass times velocity. So what this turns out becoming is d by dt of m times v, which means there's a product rule that you got to use. So you'd see that's actually v times dm dt plus m times dv dt. So you see just that one term here, the second term on the right there, is what we had before. But in fact, to analyze stuff like a rocket ship leaving our Earth, obviously the mass changing is a big deal. And your book, actually, if I remember correctly, I think the homework system has for the homework for that chapter on momentum, which I think was chapter 10, had a problem that sort of walked you through how to use this version of Newton's second law for thrust on a rocket ship, stuff like that. It's a little more cumbersome than you might have expected. But the main thing is to realize that dp dt is what's on the right-hand side of Newton's second law. Similarly, for rotation, we find that the summation of the torques is equal to make a parallel, I'm going to say it's dl dt, but in fact, L can be defined as R cross P, where P is the exact same quantity. Now, I also want to reiterate that P equals mv is not relativistically correct. So we're going to see that when we cover chapter 36, that it turns out that particular version of momentum does not work when we take into account that objects might be traveling near the speed of light. So in fact, we'll add a 1 over the square root of 1 minus v over c squared in front of it, and that'll make it actually work. But the main thing is just know that when you're dealing with speeds and energies comparable to the speed of light and comparable, of course, to energies that are like the mc squared for a particular particle, then we have to use relativistic momentum. I'll also point out that that L, which is equal to R cross P, is also a parallel to torque, which is R cross F. Okay, and it's a cross product, which I've mentioned to you is done by there's a bunch of ways you can do it, but one of the ways you can do it is do a determinant of a matrix where the top row is in fact I hat, j hat, k hat. The second row is the first vector, so that'd be r sub x, r sub y, r sub z, and then the bottom row, the third row, is in fact mv sub x for the angular momentum, mv sub y, and mv sub z, or in the case of the torque, it would be f sub x, f sub y, f sub z, okay? So you can also see that if we actually tried to do the derivative of L, just for completeness, I'm going to show you that d by dt of R cross P, turns out there's a product rule that looks just like the regular product rule. Just it's very important that you keep everything in the right order. So you can't change the orders like I did up here when I put the V in front of dm. So in this case, it's going to be dr dt cross with P plus R cross dv dt, or excuse me, dmv over dt. You can see that this is in fact v cross mv plus r cross. Now in this case, we're going to get in this, you can actually change the order at this part, but we can write v times dm dt plus m times dv dt. So all that works out just fine. Obviously, v and mv are parallel, so this part is going to actually become 0 because remember, if you multiply a scalar times a vector, you just get a vector that's either lengthened or shrunk, and if the scalar is negative, it'll actually turn around backwards. But other than that, it's pretty much the same thing. And cross products actually just pick the components of the two vectors that are perpendicular. So if v and mv are the two vectors, they're both parallel. There are no perpendicular components, so that ends up giving you 0. So I ultimately have r. Oops, I should probably change back to blue. So I ultimately have with this r cross dm dt times v plus, oops, that's supposed to be plus r cross m times dv dt. So I'm just showing you basically how the vectorness of this would pan out. The main thing though is just like we had when the summation of the torques is equal to 0, we actually find that means dp dt is equal to 0, and that's the conditions under which we had conservation of momentum. remember that's a big physical concept here that you got to understand for this course is momentum is conserved whenever the net force acting on the system is zero. So if you treat the system as one car riding down Princess Anne, and then another system as another car riding down Dam Neck, if those two cars run into each other, then there is definitely a force going from one of the systems to the other one. So momentum would not be conserved in that case. However, if you treat the system as one car moving on Dam Neck and another car moving on Princess Anne, that's the whole system, then car one can hit car two and car two can apply a force on car one. And those are internal forces. So momentum might be conserved. What really matters at that point is obviously you're going to have some friction forces between the tire and the road. We're obviously going to have weight acting downward, but the normal force is probably going to cancel that out. The main thing is at the instant of collision, if the force acting on both of those cars is fairly minor compared to the collision forces, then that's essentially approximately equal to zero. So you can treat it as conservation of momentum, at least for that instant of impact. But then after the impact, they decide, by crumbling up or whatever, they decide, our nature decides which direction they're going to go. At that point, the friction forces between the tire and the road and all that stuff will kick in. But the main thing is, yes, momentum is conserved, but only if the net external force on the system is equal to zero. And the reason why that's so is because this right here, dp dt equals zero, means that P is a constant. So P is equal to a constant. Now P is a vector, so that means it's a constant vector. So what I mean by that is it has if we're using XYZ coordinate system, it has a scalar for the X component, a scalar for the Y component, a scalar for the Z component. And that scalar is a constant, not dependent on time or position or anything like that. Okay. So that's conservation of momentum. Now, similarly, if the summation, and I said torque earlier, everybody, hopefully y'all caught that, or at least are laughing at me. That's fine. I didn't mean to write a T there. I meant to write an F there. That's what goes there. Now, what I did mean to write a towel there is this one. And that means if the net torque acting on the system is zero, then dl dt, which is called the angular momentum, as I've already introduced, is equal to zero. And the derivative of the angular momentum being equal to zero means the angular momentum is constant. So again, we get L is equal to a constant vector. And this is what we call conservation of angular momentum. And of course, the often quoted thing is an ice skater actually spinning with their arms outstretched to the side will spin at some certain rate. And if she then lowers her arms down by her side, then what happens is her angular momentum, which by the way, also has a magnitude that looks like this. Angular momentum has a magnitude that's equal to I times omega. Since that's a constant, that means I1 omega 1 is equal to I2 omega 2. And therefore, her lowering her arms is essentially taking some of those little masses, remember the sum of r squared times m, and putting them at smaller r's. So the angular momentum, or excuse me, the moment of inertia, I2, is actually smaller than I1. But the product, I2 times omega 2, has to be the same thing as I1 times omega 1. So it has to compensate by omega 2 going up. So that's what conservation of angular momentum tells us. And basically it predicts that when a ice skater is spinning with their hands out wide, she obviously has a larger moment of inertia. When she puts them down by her side or up over her head straight like this, the masses are closer to her center of rotation. The I goes down. And in order for I times omega to stay a constant, that means omega's got to go up. And that's why she spins faster. Okay. That's also, more or less the reason why when you're, for instance, water skiing behind a boat and the boat takes a turn of, let's say, radius 100 meters, if your ski rope allows you to go out 10 meters to the right of the boat, then your radius of rotation is in fact 110 meters. And because of that, that's going to be allow you a different speed, because V is equal to R times omega. You and the boat, if you're literally beside the boat, will have the same angular speed omega. So those are some of the conditions that we found. I'm going to circle them off just so we'll know what that means. There's the conservation of angular momentum. Actually, I should go this way. So that's a new expression. I know that L is equal to R cross P. That looks a little confusing, but if you're talking about, say, the angular momentum of a Frisbee, then you could say, well, that's kind of complicated because what is R and what is P? Well, what you do is you imagine the Frisbee. Let's say the Frisbee looks like this, okay? And the Frisbee is actually rotating about, let's say, this axis. And you basically take and say, okay, here's a little R pointing to a differential mass segment right there. And you could do M times V for that particular mass segment times, and then cross R with that P, which is M times V. And that would give you the angular momentum of that little part. And then you repeat that over and over and over again until you've done all the little parts. Obviously, with something as complicated as a Frisbee, which is supposed to be fairly simple, that can get quite complicated because you're going to have R's, at least on the top. That might seem pretty straightforward because all the R's are in one plane. But as you come around the side of the Frisbee, it's going to point downward, and you're going to have a different density. Remember, the edge of a Frisbee is a little thicker. The bottom edge is a little thicker than the top and stuff like that. So you take all that into consideration, but basically you can still do it. You could just do R cross P for each little part. The other thing is, of course, that angular momentum and magnitude is also this. So you might luck out and say, okay, well, let's imagine the top of the Frisbee being just a flat cylindrical disc. And we could take the whole mass and figure out what fraction of that whole mass is just the top. And we could use 1/2 mr squared for the I for that particular flat disc top. And then we can say, okay, well, what fraction is going to be the next millimeter deep? So in other words, we're going down around the edge. We're going to go about 1 millimeter thick and figure out what fraction of the mass is that little 1 millimeter tall ring that's sort of tilted at this angle on this side and this angle on this side. We could treat that as a ring and actually treat it maybe even as if it's straight up and down, because the difference would be so small between the top radius and the bottom radius. And you could keep adding that up like that, and that would give you the angular momentum as well. You just have to, again, use the I for each individual part, the disc, and then all the rings. And then the omega, of course, each of those would all be spinning at exactly the same rate, which is whatever rotation rate the Frisbee had. Does that make sense? I know it's a lot of imagining of things that we're not actually seeing in real time, but hopefully I think you can make out what I'm trying to say. Okay, that's good enough for me. All right, so those are your major equations that you're using. And of course, we can also bring into account the idea that planets, as we learned in the gravity chapter, planets actually follow elliptical orbits with the sun at one focal point. So we can imagine a focal point here and a focal point here. This distance right here is called the major axis. And if we go halfway, say from here to here, that's called the semi-major. Axis. And that's a distance A. So this one's a distance 2A. And of course, this is called the minor axis. And of course, there's a semi-minor axis as well, but it doesn't really matter that much. We don't use it that often. But I'll draw a line right. Ooh, well, that was nice. I'll draw a line right across here. And that's our major axis. Okay. Now, the reason why I'm bringing all this up is really Newton's, or excuse me, well, if you use Newton's law of gravity and Newton's second law of motion, and the centripetal acceleration necessary to maintain, say, a circular orbit, namely mv squared over r, you can actually use that to derive Kepler's third law. And that's what I'm going to do in a second here. And that gives us something we can use. The main thing is I want you to remember that if you tie a string to, let's say, put a nail in a piece of plywood where one of the focuses is, or one of the foci are, and put a nail in the other foci as well, and then connect them with a string that's longer than the distance between the strings, and then pull that string taut, you get a shape like that. Well, if you keep that string taut and keep your pen or pencil straight up and down, you can work all the way around, and that will make the actual shape of the orbit. That's the way an ellipse is made, whereas a circle is just one nail with one string and holding the pencil straight up and straight down. So it would actually trace out a circle. For a brief second, I'm going to tell you that one, the orbits of the planets are really, really close to being circular. Okay, it's a remarkable and amazing thing that Kepler was able to determine that they were actually ellipses, because the way that they differ from ellipses, I mean, from circles, is so minor that it was impressive that he caught it. For instance, I think Mercury or Mars is like the worst case scenario. Well, once we got rid of Pluto, Pluto was a little bit worse still, but now that that's not a planet, I'm not going to even worry about that. But if you took Mars or Mercury, whichever the one that was the most elliptical of the orbits of the planets, and you drew it to scale exactly like it's shaped on the board, and then you drew an actual circle right next to it, unless you had a little bit of knowledge of geometry and measuring tools, you couldn't tell which one would be a circle and which one would be an ellipse. That's how circular these quote unquote elliptical orbits are. So it's not that huge of a loss of generality to pretend for a second that we're going to let the Earth orbit the sun with assuming the sun is so massive that it's not going to move at all. Now, it's not really that massive. In fact, once we put all the planets on it, the moon actually moves on the order of a few meters constantly as a result of the tugging of all the planets. And the biggest one, of course, is Jupiter. That's the major problem. But the Earth is really a fairly small one, so it's probably not that bad of a mistake to assume it's not moving. In fact, the mass of the sun makes up maybe even more than 99.99% of all the mass in the solar system. So if you take into account the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, IKEA, actually that's a store. I forgot the proper pronunciation of the protoplanet, or actually not protoplanet, but the Plutoid. But there's a bunch of different sort of Plutoids, are dwarf planets in the asteroid belt, and then again out in the Kuiper belt, and then there's all sorts of stuff in the Oort cloud. But still, adding up all those things, some of which are even bigger than the moon and bigger than the Pluto, and adding up all the moons, some of which are huge, like the moons of Jupiter and the moons of Neptune and Uranus and Saturn, still adding up all that stuff, the sun accounts for 99.99%, and it might even be a third decimal place on there. But the main thing is it's really huge. So the sun does not move that much when the Earth is rotating it around it. So what we're going to do is we're going to pretend that the Earth is orbiting the sun and the sun's not moving at all. It's not reasonable. It's not exact, but it's close enough. So now I'm going to take my Newton's second law. The summation of the forces is equal to m dv dt. Now, there's a very specific acceleration that has to happen in order for the Earth to follow that elliptical orbit, and that is the centripetal acceleration. The only force acting on the Earth would be the gravitational attraction it has towards the sun. The space is essentially a vacuum. So on the on the left-hand side, I'm going to have G, the gravitational constant, M, the mass of the sun, M, the mass of the Earth. These are the symbols we use in astronomy, by the way, divided by the square of the distance between the Earth and the sun. And actually, I said those symbols backwards. The circle with the dot in the middle is obviously the sun. The circle with the plus in it is the Earth. Now, that's got to equal the mass of the Earth times the velocity of the Earth squared over the distance between the sun and the Earth. Now you can see already that this m of the Earth is canceled out, and you can see that that exponent of 2 is canceled out with this r over here. Now we can make use of the fact that v, oops, I don't know how I switched to red. Yeah, I do. We can make use of the fact that v, the velocity, has to be equal to 2 pi times the radius of the orbit, which is the distance between the sun and the Earth, divided by the period of the Earth's orbit. Okay, so I now can put this in this equation above, and what I will get is G m sun over r sun Earth is equal to, notice everything canceled out except for the square of the velocity. So that's going to be 4 pi squared r for the sun Earth distance squared over t squared. So if I wish to solve this, what I will get is t squared is equal to 4 pi squared over g, mass of the sun, times the r cubed. And that is Kepler's third law. The square of the period is proportional to the cube of the semi-major axis, which, remember, in a circle, the semi-major axis and the radius are one and the same. Anybody want to take a guess? What if I were to use the units for the period of the orbit as years, and I use the units for the semi-major axis as astronomical units? Can anybody tell me what this constant would be in that system of units? So you're trying to tell me if you can figure out what that 4 pi.
Be the astronomical.
What's that, James?
Would it be the astronomical?
Yes, it is the astronomical unit that we're using on that. But what I'm trying to get you to do here is you need to use at least one piece of planetary information to figure out what that constant is, that 4 pi squared over gm numerically. What's that equal to? Don't worry too much about the units. We can work that out later. But the main thing is, numerically, what would that value be if I use t in years and the r in astronomical units? So can anybody tell me, for instance, what the period of any particular planet is? Any planet orbiting our sun? Anyone? Bueller? Bueller? I will give you a hint. You may use the unit of years, which is what I'm really asking for. Does anybody know how many years it takes for any of the planets orbiting our sun to orbit our sun? I suspect we have a case where people are scared to be wrong, and that's a bad thing. I don't want you ever to be scared of being wrong. Most of our scientific discoveries come from people being wrong. So here's the deal. Earth is the very definition of a year. So the orbital period of the Earth is what we use to define a year, and it's about 365.24 days, basically. So in fact, for the Earth, we get 1 year squared. Not only that, the semi-major axis for the Earth is defined specifically as 1. So this side over here gets you 1 astronomical unit exactly. And that one's going to be cubed. So I've got 1 squared equals that crazy constant 4 pi squared g over gm times 1 cubed. Can anybody now tell me that what 4 pi squared over gm is? So 1 squared, anybody tell me what that is?
One.
Yep. And how about 1 cubed?
One.
Exactly. So what do I have to multiply by 1 cubed to get 1 squared? What do I have to multiply by 1 cubed to get 1 squared? What numerical value?
Uh,
And
2/3.
That's
Wait,
what's
are
going
you
on.
using the
Yeah,
exponent?
you're trying to figure out how to use the exponent. Yeah, I was afraid that might be happening. Would you agree that if I multiplied 1 times 1 cubed, I would still get 1?
Yes.
Yes. So what I'm saying is the constant is in fact 1 year squared over 1 astronomical unit cubed. So that's what that constant is. Of course, that's only the constant for objects orbiting our sun. So if it turns out that Kepler's third law, where the square of the period is proportional to the cube of the semi-major axis, that's actually a law that applies to the moons of Jupiter. It applies to the moons of Saturn. Jupiter has, last I checked, well over 120 moons, and I think Saturn has approaching 100. All of those obey that rule. Our moon obeys that rule. Mars's moon obeys that rule. So it's really pretty awesome that he was able to figure out that general rule from just one particular thing. Now, it turns out that once you use Newton's laws of gravity, like I did here, if you take into account angular momentum, you can get Newton's second law, which says it says the planet sweeps out equal areas in equal times. So let me attempt to show you how that works. Let me show you what we mean by that. Okay, so there's a supposed ellipse. And I'm going to say this is a semi-major, or excuse me, this is a focal point, and this is a focal point, and this one will be the one where the sun is. So if we have a planet, let's say right here on day 1, then there's a line that you can imagine stretching out from the sun to that planet. And then over here, let's say this is day 31. then that line will sweep out this way. And in fact, inside of this is like a pizza slice, and its area we'll call A1. Now imagine trying to make a pizza slice with the exact same amount of cheese, but doing it over on the other side of the sun. So let's imagine a planet, for instance, right here. Now, if the planet's right there, are we going to go through an equally small angle to get a pizza slice with as much cheese as on the right-hand side? Or we have to go through a bigger angle?
Bigger angle.
Yes. So you could actually call this, let's say, day 763, and this is going to be day 794. So you see, still it's 31 day or 30 days. Oh, actually, I should say 93 then. So it's still 30 days. So that's what Kepler's second law says. It says that A2 is equal to A1 if the amount of time is the same. Okay, so planets sweep out equal areas and equal times. You can tell, for instance, if that took 30 days, then you're going to divide that arc length from day 763 to day 793. You're going to divide that arc length by 30 days and get a velocity. Well, look how small the arc length is you're going to do for the area A1. So clearly, out here, the velocity is slow. And here, the velocity is fast. Okay. And in fact, if you want to use conservation of momentum, you could actually say, let's do it again. I'm going to draw another attempt at an ellipse. Okay. And there's my ellipse. Now, I'm trying to remember what I was trying to, oh yeah. So what I want to do here is I want to figure out basically from this, when is, or what is the angular momentum? That's probably the best way of saying it. So I'm going to put my sun right over here again. Okay. And now what I'm going to do is I'm going to show the velocity of the planet right here. So right there, the velocity of the planet, this is actually called aphelion. And that's for something orbiting the sun, of course. If it was orbiting the Earth, it'd be apogee. And of course, if it was orbiting something else, it'd be called something entirely different. So that's my vector V. My radius vector would be this, and therefore the angular momentum at aphelion would equal R cross M V at aphelion. Okay, and notice these two are actually perpendicular. So it's only perpendicular at aphelion for an elliptical orbit. If it's a circular orbit, they're always perpendicular. Now I can go over to the other side and say that the radius vector is this guy. I'm going to call this R2. And the velocity vector, I'm going to call this V2. And technically, I really should make that a little longer because it's obviously going to speed up. So that's V2. So the velocity, or excuse me, the angular momentum at perihelion, that's what this is, when it's closest to the thing it's orbiting. The angular momentum at perihelion is R2 cross MV perihelion. Now, again, this one's perpendicular as well. So we end up getting that the magnitude of the angular momentum at aphelion is equal to the magnitude of the angular momentum at perihelion. And that, of course, means that R times M times V app is equal to R2 times M times V perihelion. Because basically, remember, a cross product is the product of the magnitude. So the magnitude of R times the magnitude of P, which is MV, times the sine of the angle between them. Well, the angle is 90, so sine of 90 is 1. So this can be used, in fact, to help us find the velocity. If they give us, notice the masses cancel out too. So unless the planet's doing something weird where it lost weight from perihelion to aphelion, you don't need the masses. But if they give you, for instance, the distance at aphelion and the velocity at aphelion, they could give you the distance at perihelion and you could immediately figure out what the velocity at perihelion is. So that's the key topic here. I will tell you, your book talks about the Coriolis force, and I think it's fine for that to be in our homework. I think it's fine for that to be in our practice test, and I think it's fine for that to be in our book, obviously. But I'm not going to test you on it. Okay, so you're not gonna see that on any online test. You're not going to see it on the final exam. But do read it. And Coriolis force is not really a force; it's a fictional force, but it's more or less a result of what happens when you're using a coordinate system that's accelerating. And in fact, you can calculate that it's actually 2 times omega cross V is the actual magnitude that it comes out to be. But I'm not going to make you do that. It's an optional section, but I do think I might have put some in the homeworks. So, all right, now that we have that, I've sort of talked about all the major things that are going to be covered in this chapter. So what I'd like to do now is solve a couple problems for you, just to show you how they're done. So I'm going to say a uniform disk turns at 10 revolutions per minute. So let's start right here. I'm going to put a line like this, say a uniform disk turns at 10 revolutions per minute. Yeah, I think that's good. Or 10 revolutions per second. Let's do that one. 10.0 revolutions per second around a bearing axis, meaning it's got bearings in it, so it's actually really smooth and has very little friction. So actually, I could have written that a better way. I could say the friction force is approximately equal to 0. And it has a mass M equals, let's say, 3.00 kilograms, and radius R equals, let's say, 15.0 centimeters. And that's good enough. We'll say it's very thin. So it's a thin disk. And I'm going to say a stick uniform stick of length L equals 2R is equal to 30.0 centimeters. And M equals 1.00 kilograms is dropped on the disc such that its center is on the axis. What is the final angular speed? Okay, so in other words, we basically got like a record player or something like that spinning, and then we have a stick who just happens to be the right size, and we drop it down on the stick, and friction, of course, immediately grips the thing and causes it to start rotating at exactly the same rate as the disc is, only the disc, of course, had to slow down to do that because angular momentum is conserved. And what we're asking for is what will be the final angular velocity. So the way we do this is as follows, and actually I don't need much space, so we'll say solution. We have I1 omega 1 is equal to I2 omega 2. And basically, because the axis is frictionless or very close to frictionless, the net torque on the system is 0. We're treating the system, though, as if it's the stick and the disc. If I didn't, then obviously the stick landing on the disc would actually be a force, and that could, in principle, cause a torque, and that torque would mean that conservation of angular momentum is not a thing. It's not conserved. But in this case, it will be. So initially, we have the moment of inertia of the stick times the angular velocity of the stick, which is 0. So we're just going to say 0 plus. Now I'm going to take the moment of inertia of the actual disc, which is 1/2 big M R squared times omega 1. I'm going to write up here that this is omega 1. You can already see that M is that figure and R is that figure. Now, that angular momentum, of course, is equal to the angular momentum after they're stuck together. Well, once they're stuck together, then you have a moment of inertia. Since their axes are aligned, the moments of inertia just add. So it's going to be 1/12 M d squared plus 1/2 M R squared times omega 2. And I'm going to put that 2 right there. I'm going to put that equal to D, since I had already called it L and changed it. This is M, that works fine. So that's really what we need. So now I can see that omega 2 is actually going to be equal to 1/2 M R squared over 1/2 M R squared plus 1/12. By the way, hopefully y'all realize that 1/12 is actually the formula that we get for a rod rotating about its center of mass. And then all of this times omega 1. So this is going to be 1/2 times 3.00. I'm going to leave off the units because we're obviously running out of space. So 1/2 of 3, well, that wasn't good. 1/2 of 3, I'm leaving off the sig figs too, times the radius, which it's okay to actually leave it as centimeters. So I'm just going to write centimeters. I'm just going to write it as 15. The centimeters will cancel out, in other words, so it's not a big deal. So there's my 1/2 MR squared. And then all this is going to be 1/2 3 15 squared plus 1/12 Now the mass is 1. And I think I wrote that. Yes, I did. And the length, of course, is 15 as well. And then all that will be times omega 1, which is 10.0 revolutions per second. So I can now calculate all that, if I can find my calculator. So I'm going to take 0.5 times 3 times 15 squared times 10. Yes.
You said the length is 15. I thought it would be 30 centimeters.
Oh, no, I was trying to make the length exactly the same as the diameter of the disc. So they're both the same size, just so it just fit on there nicely.
All right.
Okay. All right. So I've got 0.5 times 3 times 15 squared times 10. I'm going to divide that by 0.5 times 3 times 15 squared. And then I'm going to add to that 1 times 15 squared. And then I'm going to divide that by 12. That'll make for the 1/12, of course. And that gives me 9.47. And I'll actually call that 474 with one extra sig fig revolutions per second. And that's the answer. Any questions on that? So you can see this is sort of like the problem that I worked in class with conservation of linear momentum, where it was like me running next to a skimboard. The skimboard had a certain weight and a velocity, and then I would try to match that speed and jump on it. And of course, I wouldn't match that speed perfectly. So my velocity and its velocity would be different. And then the end would have a very different velocity altogether, but we were stuck together. So it's sort of like the same problem, only that one was linear momentum and this is angular momentum. So any questions about that? All right, there's another problem I wanted to show you, and this one will be more like one where we're going to use the fact that a angular momentum or a torque is actually a cross product. And I'm going to show you how to calculate that. So let's say, example. I'm going to just do the brute force thing, say a particle is located at R equals, let's say 5.0 I hat plus 4.0 J hat plus 6.0 K hat, all of that measured in meters. And a force F is equal to, let's say 4.0 I hat minus 8.0 K hat. And all this will be measured in newtons, is acting on it. What I'd like to know is, what is the torque? about the origin. Notice I have to say that because the R vector is always supposed to point from the axis of rotation to the actual point where the force is applied. So in this case, I gave you a vector that pointed to the particle from the origin. So that wouldn't be the right R unless I was imagining rotating it about the origin. So here's the solution. Torque is equal to R cross F, which is equal to the determinant of, now I'm going to make a 3x3 matrix. I'm going to make the top row I hat, J hat, K hat. I'm going to make the middle row the R vector. So that's going to be 5. Notice I'm ignoring sig figs and all that stuff right now. 5, 4, 6. And I'm going to make the last row 4, 0. Notice how I had to put 0 there, and -8. Notice everything's 2 sig figs. Notice the units. Obviously, the middle row has units of meters. The third row has units of newtons. So when I go to compute this, the way I'm going to do it is I'm going to say I hat, and that is in the 1, 1 position. So if I raise -1 to the 1 + 1 power, I get -1 squared, which is of course -1 in parentheses squared. That's +1. So all I got to do is cover up the first row and the first column. That leaves me the 4608. Now I'm going to multiply top left, bottom right, and then subtract from it top right, bottom left. So 4 times -8 be -32. And then I'm going to say minus 6 times 0. That's what I get for the I hat term. Now the next one's the J hat term, and that's row 1, column 2. So -1 raised to the, in parentheses, raised to the third power gives me -1. So I handle that by doing the multiplication, the X multiplication in the opposite order. So that's the way I'm going to do it. And by covering up the first row and the second column, all we're left is the 5, 6, 4, -8 matrix. So because I'm doing it opposite because of that negative, I'm going to do 6 times 4 first, which is 24. And then I'm going to do 5 times -8 and subtract that from it. 5 times -8, of course, is -40. And now I'm going to do the K hat term. That is, of course, row 1, column 3. 1 + 3 adds up to 4. Parenthesis -1, close parenthesis to the fourth power is +1. So I can do the regular order. In this case, all that's left is the 5, 4, 4, 0 matrix. So I'm going to do 5 times 0 is 0, minus 4 times 4 is 16. And obviously, each one of these comes out in units of Newton meters. So I get -32 Newton meters I hat. That's the first component. The second component is 24 minus -40. So that's 24 plus 40. That'd be 64. Notice I am doing 2 sig figs. That's the J hat direction. And then -16 Newton meters K hat is the final. That's it. That's all you have to do cross products. Of course, I just did basically torque equals R cross F. That's certainly one of the versions that we could use, but there's another thing. Remember, we could also use L equals R cross P. That's another instance where you get to use the cross product. So remember that's another option about how you're going to calculate stuff. Of course, L is also I times omega. Any questions on that one? All right, I'm gonna now do another example. Okay, and the example is going to be basically that F is going to equal 5.0 I hat minus 4.0 J hat. And that's going to be measured in kilonewtons. And I want to calculate what is the torque about the base. So now it comes in to us having to draw a picture. So my picture is basically this. I'm going to have an x-axis pointing this way. I'm going to have a y-axis pointing this way. And I'm going to have a z-axis pointing this way. Okay. Now what I'm going to have is basically a pole that comes up and takes a turn and then goes horizontally right over the z-axis like this. And this pole is very thin, but I'm trying to show that it is in fact a pole as opposed to just a sticker or an infinitely narrow line or something. Okay, so that's that. And then on top of it is this little thing right here, sort of like a sign, you might say. And what I'm going to tell you is this force is actually acting at this point right here. Actually, I shouldn't draw it that way. I'm going to do this. I'm going to say, oops. That's the center of mass, if you will. So the force is going to act like it's all acting there. Okay. And the origin that I talked about earlier, the base, is that little point right there. And what I have is that this distance, let's see, I use black here. This distance is 6.0 meters. This distance from here to here is 8.0 meters. And I think that's pretty good. Yeah, that's enough. Okay. So that's what I want to calculate is the torque. So the torque is supposed to be R cross F. And I should put a vector symbol up here. So I'm going to start off with solution. Whoa. The torque is supposed to be R cross F. So that means a vector that actually points from the axis of rotation or the point of rotation to the actual point of application of the force. So I've got to first form the actual vector that points from O to the CM. So what I'm going to do is I'm going to say O CM is going to be, in fact, notice the center of mass has a y component, of 8 and has a, or I should say y position of 8 and a a z position of 6 and a x position of 0. So I can actually say the final point will be 0, 8.0, and 6.0. And the initial position, of course, is 0, 0, 0. So this is actually the process that you can use to find a vector. If you want to find a vector, one thing you can do is take the coordinates of the head of the vector, which is the first thing I wrote down, and subtract from it the coordinates of the tail of the vector, which is the second ordered triple that I put down. So I can now say that R is going to equal 0 minus 0. So that's going to be no I hat component, but I'm going to have an 8.0 meters J hat and a 6.0 meters K hat. And that is my R vector. So now all I got to do is compute the cross product, which again is the determinant of a matrix. And in fact, I'm going to say I hat, J hat, K hat. And now the R is going to be 0, 8, 6. And the F is going to be 5, negative 4, 0. That means my I hat component, you can see, is 8 times 0, which is 0, minus 6 times negative 4, which is negative 24. My J hat component is going to be, that's the one that actually has the negative. So the 0, 6, 5, 0 matrix that I get, I have to do in the opposite order. So I'll do 6 times 5, which is 30, minus 0 times 0. And then finally, my K hat vector, that's another one that's positive, so there's no problem with that. My matrix is 0, 8, 5, negative 4. 0 times negative 4 is just 0. And then minus 8 times 5 is 40. So ultimately, I get that the torque is going to be equal to 24 kilonewton meters I hat plus 30 kilonewton meters J hat and minus 40 kilonewton meters K hat. That's going to be the final torque. Any questions on that? Easy peasy, right? All right, so I'd like to work another problem. If no one has any questions on that, I think I'm going to do this. So let's say example. So I'm going to first off draw the Earth. Okay. And I am going to draw right in the center, the North Pole. And I am going to imagine that something is going to run into it right here on the equator, such that this angle, which by the way is also parallel to this angle, this right here is 45 degrees. And I'm going to say this object has a velocity v pointing that way. And that velocity is equal to, let's say, 3.0 times 10 to the fourth meters per second. So we're talking on the order of tens of kilometers per second. That's pretty darn fast, but that's also very much close to the escape velocity for the planet. It's also pretty close to what the velocity of a meteorite would actually be, because it turns out a meteorite is going to be attracted by gravity. And if it comes from infinitely far away, the speed that it would attain in reaching the surface of the Earth, if it was attracted by the Earth all the way, would be essentially the same thing as the escape velocity. So that's a pretty reasonable assumption. I'm going to say the mass of this thing is actually 6.0 times 10 to the 10 kilograms. Okay, so that's the mass. And what we're going to imagine is whether it's going to affect the rotation of the Earth. So actually I should write this in blue. Will this collision appreciably affect the Earth's rotation rate? Which is approximately, well, actually, let me do this. I'll say omega is approximately 360 degrees divided by 23 hours, 56 minutes, which actually is pretty close to 360 degrees per day. But that there's actually a small difference in that, because that's the difference between a sidereal day and a solar day. So I just wanted to make that point to you guys. If you imagine the Earth actually orbiting the sun, and you actually stuck a vertical pole on the equator and had that point towards the sun, that would be essentially noon. And if we happen to do it on the vernal equinox, then that would mean that vertical pole on the equator would cast no shadow at noon. Now the Earth is going to not only rotate from there to the next day, it's also going to move to the side. And in rotating, once it goes a full 360 degrees, that stick that originally pointed to the sun no longer points to the sun, but it's still pointing to, say, Arcturus, if that happened to be right behind the sun. So if you look right behind the sun and you happen to see the star Arcturus, which is, thousands of light years away, then that stick would point back to Arcturus after doing a 360 degree rotation. And that's called a sidereal day. And that takes 23 hours, 56 minutes. But a solar day is the time from noon to noon. So it has to actually rotate an additional 0.986 degrees to get back to noon. And that's, of course, the 24-hour day. So the sidereal day is 360 degrees, 23 hours, 56 minutes. But the solar day is 360.986 degrees and lasts 24 hours. Okay. All right. So what we're going to realize here is that we need the radius of the Earth. And of course, we can quickly look up the radius of the Earth. Actually, I say we can quickly, but I'm not sure that we can quickly. But basically what I'm going to say is the moment of inertia, or actually I should say angular momentum is going to be conserved. We're treating this system as the asteroid and planet Earth. So the angular momentum before, do solution. The angular momentum initially is equal to angular momentum finally. Now, the angular momentum initially is going to be basically the radius of the Earth times, I think you can see that this distance right here, since this is the radius of the Earth, this distance is radius of the Earth times cosine 45 degrees, which of course is 1 over the square root of 2. So radius of the Earth cosine 45 degrees times the mass, which is 6.0 times 10 to the 10th kilograms, times the velocity, which is 3.0 times 10 to the 4th meters per second, plus, this is all L initial, by the way, plus the angular momentum of the actual Earth. And the Earth, we're going to pretend is roughly a sphere. So it's 2/5 times the mass of the Earth, which I wish I had my book with me. I could look these things up really quickly. If someone wouldn't mind looking up the mass and radius of the Earth for me, I'd be very appreciative. But it's 2/5 times the mass of the Earth. Actually, let me see if I can do it real quick on the internet, on the interwebs. Okay, so the mass of the Earth is 6 times 10 to the 24th kilograms, and the radius of the Earth is 6.4 times 10 to the 6 meters squared. And then, of course, the angular speed is 2 pi radians. I'm going to say in essentially 24 hours. So that'd be 24 hours times 3,600 seconds. So that'll actually give me the right units, because when I multiply 3,600 seconds per hour times 24 hours, that just leaves seconds in the bottom. So I can say the total angular momentum before is going to be, only got a couple minutes left. So 6.4 times 10 to the 6. That's the radius of the Earth, times cosine 45 times 6, 10 to the 10th, times 3 times 10 to the 4th. That gives me 8.15, 8.146 times 10 to the 21 kilograms meters squared per second. That's just the first term. Now the other one is 0.4 times 6, 10 to the 24 times 6.4, 10 to the 6. That's going to be squared, times 2 times 3.14159 divided by 24 times 3,600. This one's going to give me 7.149 times 10 to the 33 kilograms meters squared per second. So that's the angular momentum of 4. Now afterwards, the angular momentum final is going to be 2/5. So basically the whole mass of the meteorite or whatever, the asteroid, is just going to become part of the Earth, and the Earth's not going to have an appreciably different shape. So it's going to be 2/5 m, only now the mass is slightly larger. We might not even be able to see it. Actually, we can't see it. It's 14 decimal places back. So I'm going to say it's 6.0 times 10 to the 24th kilograms times 6.4 times 10 to the 6 meters. That's going to be squared times omega final, which is what I want to know. Okay. So I can add these two. And basically I'm going to get essentially nothing, because it's 10 to the 21 added to 10 to the 33. So obviously we're going to be about what, 12 decimal places in before you'd actually see anything, and mine doesn't even go up to 12 decimal places. So what we're going to find is omega final is essentially equal to 7.149, or actually let's say 148862578 plus, now we're going to go to a buttload of decimal places, but basically 0.000000000, that's 9, 10, 11, and then 12. I'm going to add to that 8146. All of that times 10 to the 33. That's just the mass part. And then that's kilograms. Whoa. And then times 6.4 times 10 to the 6 meters squared. That's basically what's going to be the top, and then the bottom is going to be divided by basically the same thing, but just with the 7.148862578 times 10 to the 33. So that's basically what's going to happen. So no, the angular speed will not be appreciably changed. Okay, that's it. Anybody have any questions? It's now 42 after, so obviously we've gone 2 minutes over. You guys are welcome to split. I'm going to wait here for the last person to leave. I'm going to stop sharing unless, does anybody need me to not stop sharing? I mean, I'm obviously going to post it in a few minutes, but otherwise I'm just going to kill it. Still going to post it though. Okay. So does anyone have any questions for me? I know I have one student that needs to speak with me in private, so I can go off into a breakout room and do that if necessary. But right now I need to find out if anybody else has any questions. So it looks like nobody has any questions. James or Carter or Randall, which one of you guys needed to speak with me? I can go ahead and